So we've used tangent lines in the past to approximate function values. But when we use a tangent line, right, they're 1-degree linear equations, hence, calling them tangent lines. So they're only close to the curve for a really small section near the point of tangency. So like, for example, we have the curve y equals sine of x here, and then this is the point pi over 3, x equals pi over 3 here. Right, so if you zoom in really close, right, the line and the curve are really close to each other for a certain angle, right, for a certain interval, but then you have all this space in between them as you get out here. So they get further and further apart from each other as you get further away from the point of tangency. So every time that you've written a tangent line so far, you've actually been writing something called a Taylor or Maclaurin polynomial, depending on where you're centering your point of tangency. So technically you already know how to do the skill that we're going to cover today. So we're going to expand the idea of a tangent line approximation to higher degree equations. So think quadratics, cubics, quartics, quintics, and so on and so forth. So down here I have the red graph is still y equals sine of x. You can see that the labels are color coded to the graphs here. So we still have y equals sine of x. This is still x is pi over 3. I don't know why my pen is being weird today. Okay, we'll try that instead. I think that angle of writing is a little bit better. Okay. Right, so it's hard to see because of the quality of the image, right? But you can't even see the red y equals sine of x curve underneath some of these Taylor polynomials. So the blue line, right, is the same as the blue line above. It's your tangent line approximation. That's the first degree Taylor polynomial, right? So straight line, there's a lot of gap between the red curve and the blue line. The black curve is a second degree polynomial. It's a parabola centered at pi over 3 for the approximation. And you can see that it's pretty close, right? You have some space going on down here where there's some distance between them and over here, but close to pi over 3, they're pretty close together, right? And then we have the green graph, which is a third degree Taylor polynomial. So it's even closer, right? Around here, you can't even see the red graph for a while underneath the green graph, but you can see how there's kind of less distance between the red and the green graphs than there are between red and black or red and blue, going down in degrees of accuracy. So these are all what we call Taylor polynomials. And what a Taylor polynomial is it says if, whoops, I don't want to write it in a highlighter. If f of x is a function with n derivatives, then the following polynomial, we're going to call this p sub n, where n stands for the number of derivatives of x, is equal to, we're going to do f of c plus f prime of c times x minus c plus f double prime of c all divided by 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c cubed plus all out to the nth derivative at c divided by n factorial times x minus c to the nth power. This is called the nth degree Taylor polynomial. And it's centered at x equaling c. Whoops. Let me just zoom out so you can kind of see the whole thing there. So this n stands for the number of derivatives that you're going to take, right? That's why these n's are here. And then c is your center point. So c is what we plug in for all of these locations. So the formula for the polynomial is always the same. It's just going to change depending on what your derivatives are, what the derivative values are at c, and then so on and so forth. So it's always the nth derivative at c divided by that same n factorial value times the x minus the center point all to the nth power. And then it's the same thing for a Maclaurin polynomial, except Maclaurin polynomials are just Taylor polynomials centered at 0. So Maclaurin polynomials are Taylor polynomials centered at x equaling 0. So the c value is always 0. So before we get into some examples, let's talk about who comes up with this stuff. So, right, we have Taylor and Maclaurin, so Brooke Taylor and Colin Maclaurin. So Brooke Taylor was born in 1685. He was an Englishman, and he graduated from Cambridge University with a law degree, and he was also engaged in mathematics there. So in 1712, he stated his method for infinite series, but he was also elected to the Royal Society and appointed to the committee to adjudicate the dispute between Leibniz and Newton concerning who, discovered calculus. That was always a big argument. So Taylor is given credit for conceiving the concept of calculus of finite differences, the tool of integration by parts, so we've learned about that before, in Taylor's series representation. He died at age 46. And then Colin Maclaurin was born in 1698, so they were roughly born around the same time, and he was born in Scotland. So he was a child prodigy who at the age of 11 became a student at the University of Glasgow, and at the age of 19 he was elected to be a professor of mathematics. So 2 years after he became a professor, he was elected to the Royal Society of London and came to know Isaac Newton. And it was Newton who recommended to the University of Edinburgh that Maclaurin be made a professor of mathematics there, which he was when he was 27 years old. So think about that. He was really young. So in 1740, he shared a French Academy of Science Prize with Leonard Euler and Daniel Bernoulli. And in 1742, he wrote a 2-volume treatise defending Newton's mathematics as a rebuttal to Bishop George Berkeley, who claimed that Newton had used faulty reasoning. So this is the book in which the special case of Taylor series appears, and that's why we call it Maclaurin series. So he has a title for Maclaurin series, but it's really only a special subcase of Taylor polynomials and Taylor series. Maclaurin also died really young at age 48 due to his health.